Hello everyone, let's continue our lecture in function analysis. Today we will talk about bounded linear operators. Let's start with operator. What is linear operator? We have operator T, which takes map numbers from set of X to Y. And X or Y are normed vector space. We know already what is vector space. Vector space is like linear space which satisfies linearity and 8 axioms. And normed means like we have 3 conditions: positivity, like symmetry, and triangle inequality. We talked about normed space in previous lecture. What does mean linear operator? It means T is linear if for all x, y from x, tx plus y is equal to tx plus ty. And second, t alpha x is equal to alpha tx for all alpha real. So if T is linear map, linear operator, I can like write Tx is equal to Tx. This is same notation. Okay. Let me give you one example. For example, like differentiation operator is linear because when we take differential of the sum of two functions, it becomes like sum of differentiation of each function. Or when we multiply by x by lambda, we can take out lambda. So this was about linear operator. Now, what does mean operator T is bounded? Second thing which we talk, it means if norm Tx in y is less or equal than C times norm x in x, space of x. Okay, because our like another way we can write it like this, like it was Tx equal like it was T from x to y. Like bounded means we can bound this relation here because the space of T is y and divided by x by some constant. The third thing about linear operator, T is continuous at point x0. What does mean? By definition, it means if for given epsilon greater than 0, there exists delta which depends from epsilon and x0, such that for x minus x0 in x less than delta, tx minus tx0 is less than epsilon with respect to y. So it means when we take two numbers, if they are close to each other, then the linear operator will be also close. Let's prove main theorem in function analysis, like fundamental theorem. We have linear operator T from space X to Y is linear. Then this three things is equivalent. Following are equivalent. T is continuous. Second, T is continuous at point 0, and the third thing is T is bounded. All of them are equivalent. So from the first to second, it's obvious because if T is continuous, then T is continuous in each point, then one of these points is 0, so T is continuous at point 0. And from second to third, let's prove. Like we know at the point 0, T is continuous. What does it mean? There is delta, exists delta, such that norm x minus 0, okay, x in x less than delta, so tx in y is less or equal than norm x minus 0 in x. Just a minute. Oh, tx minus tx0, which is in our case 0 because t0 is 0, should be less or equal than epsilon. Let's here I take epsilon. So let's fix y from x, and ty will be like ty divided by delta times delta y divided by y, norm y. We know by definition of linear operator, this is equal to norm y divided by delta times t delta y divided by y. So we know that like this is less or equal than delta, because y divided by absolute value of y is less or equal than 1. So we get ty in y is equal to y divided by delta t delta yx divided by delta. So we take constant 1 over delta, so we get ty in space of y is less or equal than cy in x for all y, small y's. So we got bounded. Y here becomes like yx because we are taking y from this set of x, and when we take norm from both sides, it becomes like norm of y. So let's prove from second to third. Now we have we have proved from second to third. Now so we have t x minus y less or equal c x minus y. Okay, now we have t linear, we said bounded operator t from x to y. Then what is operator norm? Operating norm is t equal to sub tx in y divided by x in x for all x in x when x is not equal to 0. This is equal to sub tx in y. We can take norm of x in x, assume that is equal to y 1. This is x supremum tx y when norm x is equal to 1. So supremum tx, let's prove it. When x less or equal than 1, we can write it like supremum tx divided by x. Why we can write it like this? Because we know that 1 over x is greater than equal to 1, we just divided by this one. So this is equal to supremum tx divided by t x divided by x. This is equal to sup tx when norm x is equal to 1. This is less or equal than supremum tx when x less or equal to than 1. So we get proposition if t is a norm on the vector space Lxy, so we can write it like tx from x to y bounded and linear. So what it means? T plus s x is equal to x plus sx and alpha tx. Now let's prove another theorem. If y is complete, then our Lxy is complete. What does mean complete? It means all Cauchy sequence converges. Tn, let's assume Tn is Cauchy. So we fix x from x and consider Tnx as a Cauchy from y. So we have to prove that Tnx minus Tny converges. We know that this is less or equal Tn minus Tm x. We know that y is complete. It means exists y which is limit Tn x is equal to y. So it means x converges to y tx. So this define t from x to y is linear bounded. So Tn minus t and Lxy goes to 0. So here we can do some summary. We have L, X, Y. This is normed vector space with norm T in LXY is equal to sup TXY divided by X in X when X is not 0. So first thing, if Y is complete, LXY is complete, so it's Banach space. TXY less or equal T, we can write it like TLXY times norm X in X. And second thing, we can write, for example, if we have linear map from X to Y and another linear map from Y to Z, then T belongs to LXY and S belongs to LYZ. The composition is TX equal STX. How we will prove it? Like norm STX is equal to STX Z less or equal S in YZ and TX in Y. This is less or equal S in LYZ, and we can write T again in LXY because our norm in our space T, it's like this, times X in X. So we divided by X norm X, so we get STX and Z divided by norm X is less S YZ times T. So we proved that ST norm in linear space XZ less or equal norm S in XZ times T in XY. Okay, the next topic is about duality. It's dual space, and we will talk about it later. Thank you. If you have any question, you can write, comment.